All right. So today's speaker is Ruth Lieberman, and she received her PhD in atmospheric science from the University of Washington. And then she was a postdoctoral research associate at the University of Michigan, working on NASA's UR satellite mission. She then spent 15 years as a senior scientist at Northwest Research Associates, working with the timed AURA and AIM missions before moving to GATS. She managed NSF's astronomy program from 2016 to 2018. And in 2018, she joined the Ionosphere, Mesosphere, or Thermosphere lab at Goddard Space Flight Center. And Ruth's work involves satellite data analysis of planetary waves and tides and their coupling to the thermosphere and ionosphere. And today she will present on lunar tide in the thermosphere and ionosphere. So please go ahead, Ruth.
All right. Thank you very much, Nick, for that introduction. And thank you for inviting me to be the colloquium speaker today. So this work was motivated by my decision to use the lunar tide, the atmospheric lunar tide, as a marker of vertical coupling. And so basically this talk is going to be a discussion. It's going to be a defense of my analysis of the lunar tide in these data sets that I will be talking about, and why I felt that it was a suitable marker to investigate coupling between the thermosphere and the ionosphere. So to get started, I thought I would just briefly review the atmospheric lunar tide. So like the solar tides that we're more familiar with, at least at these kinds of colloquia, the lunar tide is basically a global scale inertial gravity wave on a sphere. And it is forced primarily from the basic source is the Earth-Moon gravitational attraction, and the tide is the difference between that force over the surface of the Earth and the force at some concentrated reference point. So let's see, I don't know if you're seeing my pointer here, my cursor here. So for example, in this top little diagram, the arrows show the gravitational attraction between the moon and the Earth, which is clearly stronger on the moonward side of the planet compared to the anti-moonward side. And if you subtract from these arrows the force calculated at the center of the Earth, then you wind up with this difference pattern in the lower cartoon, which clearly shows the excess force on one side, the deficit on the other side, pointing radially outward, and then this radially inward, pointing net force. And so that is the tide raising force, this difference that we're seeing, which kind of results in a net squishing of the Earth. So with that, then, the primary mode of the lunar tide, which is called M2 in the literature, it is a wave number 2 pattern in longitude, because of these two bulges, and it has a period of 12 lunar hours, which is equal to 12.42 solar hours. And when modelers consider the lunar tide, in addition to this tide raising potential that I've just talked about, that's concentrated at the surface of the Earth, they generally include some other forces. Modelers will usually include the surface stresses due to the tidal motions of the ocean and the solid Earth. So it's these motions, forcing the atmosphere at the surface. And they also include something called ocean tide loading, which is the deformation of the Earth due to the weight of the ocean tides. And this apparently kind of modifies the distribution of gravity at the surface. And as I said before, dynamically speaking, the lunar tides are basically global scale inertia gravity waves. They propagate vertically wherever the frequency, the lunar tidal frequency, is greater than the Coriolis frequency, or if there's a mean wind, greater than the, greater than the Coriolis frequency modified by the meridional shear. In a windless atmosphere, this would imply that the lunar tide vertically propagates practically everywhere on the globe, except maybe within a degree or two of the poles. So the vertical wavelength is, runs between 40 and 50 kilometers below the turbopause. Above the turbopause, the wavelength, it lengthens. And, just like in classical gravity, inertia gravity wave theory, amplitudes generally increase exponentially with altitude up to about the turbopause. So I thought I'd show a few pictures here. The plot in the upper left-hand corner comes from Zhongforbes, 2013. They analyzed lunar tides in UR's mesosphere and lower thermospheric winds from the Hardy instrument. And, they look very much like pretty classical tide plots, downward progression in local time. And the amplitude of the lunar tide in the zonal wind is about 10 meters per second in the lower thermosphere. Now, over to the right, from the same Zhongforbes paper, is the seasonal variation of the lunar tide at 111 kilometers. And it suggests a summer time, a summer hemisphere maximum at middle to upper latitudes. And this plot down here is I just grabbed from Wacom-X, and it just illustrates the vertical wavelength lengthening of the tide. Now, in the ionosphere, I'm showing a plot from a paper by Nick Penatello from 2014, showing M2, the lunar tide, in cosmic F-region maximum electron density. And there are some pretty interesting differences between this plot.
Ruth, I don't mean to interrupt, but I think we are not seeing the slide that you're referring to.
Oh, that's not good. Did you see the ones previous?
Yes, at least for
seeing...
me, I see the one with Hardy zonal wind.
Yeah. Now you mean to tell me that you're not seeing the one with cosmic NMF2?
No, at least I don't. I don't know if anyone else is.
Is anyone seeing it? All right.
No.
Oh yeah, now it just took a long time to advance.
Okay, so did it pop up? Is it up now?
Yes.
Okay.
Go ahead.
All right. I guess it's a big JPEG or something. I don't know. Anyway, so this is this is a picture of M2 in the ionosphere, and it looks to my to my mind quite different from the way the UR's plot looked for the same projection, as a function of month versus latitude. For one thing, the maximum in the summertime maximum in the high latitudes, middle to high latitudes, seems to have done a disappearing act on us, or at least it's greatly watered down. And the most prominent features turn out to occur on either side of the magnetic equator, at around 20 or 30 degrees. And what this behavior seems to suggest is that the imprint of M2 on the plasma looks quite different from that upon neutral variables. And so that in the ionosphere, M2 is going to be controlled not only by inertia gravity wave dynamics, but also by electrodynamics. So that then brings me to, the motivation for this work and for the presentation. I wanted to use some of the new measurements of the thermosphere and ionosphere from ICON and GOLD to characterize M2, the semi-diurnal lunar tide. I wanted to use these new observations to characterize M2 in the thermosphere and ionosphere, and to see if they would help us kind of get our hands on the mechanism for coupling the E region to the F region. And I chose M2 as the tool, as the tracer, for several reasons. It struck me as being a very clean tracer because its forcing is known. It's fully concentrated at the surface. It's external. There's no like an internal forcing, no instability involved, and so far no nonlinear, generation or anything like that. So it's its source is well known. It's vertically propagating, so we know how it gets from the surface to the lower thermosphere. And importantly, it is fully sampled by ICON and GOLD, despite the fact that both instruments make a lot of their measurements only over part of the day. A lot of these measurements are either daytime only or nighttime only. So with that, I'll lead into the discussion of the lunar tide analyzed in the GOLD data. So GOLD is a spectral imager, observes the far ultraviolet spectrum in the Earth's atmosphere. The instrument is hosted, it's a hosted payload. I think it's on some communication satellite. It's in a geostationary orbit, which is pretty unique for upper atmosphere observing. It launched in October 2018, and I'm going to start off by showing the lunar tide in GOLD thermospheric disk temperature, day-side disk temperature, which is associated roughly with the 160 kilometer level. So these three panels at the top here, they're just more or less random plots of GOLD. They're taken all on the same day, 1 hour consecutive. I think somebody in the community just asked me for this, because they wanted an easy way to grab GOLD data quickly. And so this shows GOLD's sampling. GOLD observes the Atlantic and South American, the Atlantic and the American sectors. And so a few things kind of stand out from these plots here. The temperatures are very high. We're like 600 K. The background temperatures are very high. GOLD is seeing perturbations. You can see them in the plot. And recalling that the magnitude of the lunar tide of M2 was about 10 meters per second at 110 kilometers. And so expecting that it's about the same order of magnitude for temperature at 160, you appreciate very quickly that we're going to have to find some way of subtracting out the background temperature, very, very cleanly, if we want to try to nail down something with an amplitude on the order of 10 degrees, or even less, as we'll see. So at any one point observed by GOLD, the lunar day is sampled by GOLD over, for the temperature measurements. The lunar day is sampled by GOLD over 15 Earth days. And I've tried to kind of show that here in this plot down here, where I've simply, shown all of the lunar local time sampled. Actually, it's 24 hours that's sampled, 24 lunar local hours, but I just fold the 12 to 24 hours back into the 0 to 12 because I'm interested in the 12-hour oscillation. So there should be about, 15 symbols along each axis here. Anyway, so the nice thing about gold is that while it's sampling the lunar tide at every point, it's keeping the solar local time fixed. So if I take the average over the all of those lunar local times sampled, if I take and subtract the average from the reported temperature, I am getting rid of not only the time invariant temperature, that's the 600K part, but I'm also getting rid of the solar tides. And that's important because given that the lunar local tide has a period of 12.42 solar hours, which is very close to the solar semi-diurnal tide period of 12 hours, the two, and given that the dynamics of the lunar and the solar semi-diurnal tides are quite similar, the last thing we want is to have a lunar tide a lunar tide analysis that is messed up with solar tide analysis. So I do the averaging that I describe here, remove the background, remove the solar tides. That will leave us with a residue of a data set, which will still have all sorts of interesting stuff in it, but it won't have, the time invariant part, and it won't have the solar, the solar varying part. That residue, I bin in lunar local time bins, and then I just fit a 12-hour curve to it, which for the particular latitude I chose, seems to be a very good 0th order fit. So I do this for all of Gold's points, average them in longitude. It's not a full average because Gold only samples really kind of a sector, but it's my effort to get the migrating component of the lunar tide. And so this is what we wind up with. As a function of local time and latitude, this is the M2 temperature pulled out of Gold temperatures. And it is its amplitude is 4 degrees. And it does, seem to have a global and globally coherent kind of a structure. I never really, before I worked on this, I didn't have any clear idea of what M2 should really look like at this altitude. And I decided to compare with WACM-X. Nick made a run that was calibrated to icon and Gold solar and geomagnetic conditions and to MERA meteorology. And I managed to convince myself that the that the M2 analysis in Gold is real, based on what I consider to be pretty decent agreement with WACM-X. Enough agreement to give one confidence, and enough disagreement to make the data analysis important or at least interesting. So the purpose of the lunar tide, the purpose of the lunar temperature tide analysis was pretty much just to convince myself that the methodology works. Since Gold only samples at one altitude, I really can't say an awful lot about vertical coupling, at least not strictly from the data. The information from more information about vertical coupling might come from looking at the 135.6 nanometer air glow in Gold. This is an emission that is associated with the recombination of ionic oxygen with electrons, which takes place up in the F region. And it, too, is one of these very clean-looking kind of signals. It is very reminiscent of what we saw, the figure we saw in Nick's paper of the electron density. It is, it maximizes on either side of the magnetic equator in the evening, at night, actually. And here I've plotted it straight from Gold as a function of the solar local time, which isn't telling, which maybe tells us a lot. But of course, it's the lunar tide that I want. So I basically took all these data and analyzed them into the M2 projection. And so we get something, very similar looking in the lunar tide. So it appears that in the 1356, the lunar tide is basically the signature of the equatorial ionization anomaly. That's what this, that's what the air glow emission is sort of a proxy for. It's the phenomenon of it's believed to be the phenomenon of particle uplift from a large reservoir in the E region, uplift due to the E cross B drift associated with the E region electric fields. That's what the E stands for, and their migration along magnetic field lines, which have to occur on either side of the magnetic equator, since magnetic field lines are completely horizontal at the magnetic equator. So it appears that we found M2, in Gould's, equatorial ionization anomaly proxy. And so now what I'm hoping to do is close this loop, this process loop observationally, by seeing if we can find evidence for the E region electric field, which is thought to originate dynamically, which is thought to be basically a dynamo driven field, driven by neutral wind motions in the lower thermosphere. So basically the next thing I'm going to try to go after is the E part of this E cross B drift, which is thought to be the source of the electrons and ions that participate in the recombination that produces this signature. So to go after the electric field, or a proxy for it, we now turn to the Ionosphere Connection Explorer, or ICON. ICON launched in October 2019, and it is a mission that was basically designed to do, to look exactly for this, to observe and to measure E region winds and dynamo-driven, and the E region dynamo and its uplift, and the velocities associated with the uplifted particles. So it does this by measuring neutral winds between 90 and 300 kilometers. And it also measures the ion velocity at spacecraft altitude. So the analysis of M2 in ICON proceeds similarly to that in Gould, which is to say, one wants to first try to find a way to average out a large background associated with the time mean and the solar tides, but there's a catch. The good news about MIghty sampling, MIghty is the wind measuring instrument on ICON. It's a Michelson interferometer. So the good news about ICON sampling is that it covers the lunar day in only 9 Earth days, as opposed to 15 for Gould temperature and 27 or so for the 1356 emission. So MIghty sweeps out the lunar day kind of faster. But the bad news is that the local time is drifting during that 9-day period. So if I can remove the time invariant background over those 9 days, but I can't completely remove the diurnal tide because its phase moves a bit. So I basically collect 3 different sets of 9 days, because the problem is that over this particular set, I'm going to have a solar tide residual, representing roughly the 16 to 19 LT phase. And so I basically repeat this 9-day averaging 3 more times, so that I kind of cover the whole range of solar local times, and so therefore, hopefully wash down this solar tidal leakage. And that's important, because the solar tides are get to be pretty large over MIDI's observing region. MIDI, I'm showing here only the altitudes where MIDI can provide 24-hour measurements. And so in between, even between 100 and 115 kilometers, the diurnal tides are significant, and they're quite big in the in the red line. In the region sampled by the red line between 200 and 300 kilometers. So, do we dare go through with this? So here is M2 zonal wind at 114 kilometers, and it looks, reasonable, I would say. Has an amplitude of about 6 meters per second. Seems coherent. The figure on the lower panel is my attempt at estimating the aliasing by the solar tides due to all those effects I just talked about. I clearly couldn't get rid of it totally, but it is fortunately minimal at the equator, which is nice. And even where it gets biggest, it is maybe about 20% of the lunar tide. So, ever the optimist with the rose-colored glasses, I persuaded myself that the tidal and that the M2 analysis in ICON is valid. And I also made the comparison with WACOM-X again. And again, there are a few subtle differences, mostly in phasing, but in terms of amplitude and mostly phasing, I again, convinced myself that the M2 analysis for the ICON winds is valid. So the next thing we want to do then, the next thing I did was to map the zonal wind, the east-west wind, into magnetic latitude. Because now what I'm going to do is just kind of use this zonal wind as a proxy for the dynamo-driven electric field. The idea is that the winds push the ions along with them and separate them from the electrons, which are oscillating much more rapidly around magnetic field lines. So the westward wind at this phase would then generate an eastward electric field, which through E cross B drift at the magnetic equator, where B is completely north-south, would be expected to generate vertical drift. So the bottom panel is the vertical component of the E cross B drift that is provided or derived from ICON's IVM, ion velocity meter. So this is the measurement at spacecraft altitude. And I felt it would seem that there's...
Ruth, I apologize to interrupt again. I think there's a bit of delay between your slides advancing.
Okay.
So I don't know if you want to try maybe turning off the video to see if that helps.
Oh, well, gosh, thank you for suggesting that. Hold on, I'm going to end the show here. I completely forgot that I had the video on, and you are probably absolutely right.
That might help just make it a little bit...
Absolutely.
Keep the slides
now how do I...
sort of advancing, right? There you go.
Okay, great, thanks. Sorry about that. All right, back to this. Full screen. Okay, everybody seeing this?
Yes, you have the plot of M2 in the E cross B
Yeah.
on the bottom, right?
Right.
Okay.
So
Go
as
ahead.
I said, I kind of what I did, so I arm waved my way through a, through the rationalization that this westward wind would correspond to an eastward electric field, which would then be associated with a upward, vertical drift, which seems to be very consistent with what ICON's ion velocity meter is showing. Now, another source of vertical drift has been proposed in the vertical component of the field aligned particle drift. And again, since magnetic fields have strong north-south components, have a strong north-south component at low latitudes, I thought that perhaps the M2 meridional wind could be a source of charged particles. And so I plotted out here the meridional wind associated with M2. And the lower panel is the field-aligned ion velocity at spacecraft altitude. So even though there's almost 350 kilometers altitude separating these two measurements, I was really struck by how similar the morphology looks. You've got this kind of, tilted structure with respect to latitude, particularly in the northern hemisphere, in the, M2 meridional wind. And the field-aligned ion velocity looks really quite similar, except for some phase shifting. I actually don't have any real clear sense of how these things ought to look. This isn't exactly my specialty, but in any case, looking at these two plots, one might think that the lunar tide, meridional wind could be an additional source of field-aligned particle drift. And the upper panel in this plot is the vertical component of the field-aligned motion. So that obviously is zero at the equator, but kicks in zero at the magnetic equator, but kicks in away from the equator. And so this vertical drift seems to, be very much in phase with the E cross B drift, at least in the northern hemisphere. And so so now these plots are basically just comparing the equatorial ionization anomaly with the vertical drift. So it is the ionization anomaly seems to be very much in phase with the with the E cross B vertical drift, and slightly out of phase with the field-aligned drift. It follows it, which again, I don't have any real, maybe there are modelers out there that have, a better sense than I do of what this should look like and how this should be phased, but it just seems to be, I don't know. I mean, it seems to make a rough sort of sense to me that the signature of the signature of the charged particles at in the F region would delay, that in the, well, perhaps not. To me, it makes a bit of sense that that there would be a delay between these, but I can't say. Maybe modelers know more. And finally, these are my last two slides. I'm just closing with some plots showing the temporal variability. All of these plots that I've been showing that have been focusing on the processes have pretty much been confined to February and March 2020. And with good reason, because this is a time section for the year 2020. Because, as we see in the top plot, which is the gold air glow, gold had a, relatively speaking, a prominent air glow emission exactly at that time in February and March 2020. And it's gratifying to see that the drifts also have some signal at the same time that the EIA is showing up well. So that's kind of nice. But on the other hand, there's clearly not a linear relationship, and perhaps not even a simple relationship between the drifts and the air glow, because we've got some, drift signatures here during the summer months where the air glow barely registers. And as for later in 2020, this plot just basically wraps late 2020 to the first 4 months of 2021. And again, there's this kind of, nonlinear story that the plots are telling. Strong drift does not necessarily coincide with bright, with 1356 brightness in gold. And strong and bright emissions in gold don't necessarily correspond to strong drifts. And here one wonders whether they correspond to any drift at all, except for perhaps the field aligned drift. So anyway, that's pretty much it. I've kind of summarized everything but the kitchen sink here, but all I'm going to amplify here is that I believe that M2 was credibly identified in neutral winds, ion velocities, temperature, and the 1356 air glow, and what agreement, and I say this based on what agreement there was to be had between the observations and the WACOMEX counterparts, and that the neutral wind at 114 kilometers, close to the peak of the region of Hall conductivity, the neutral wind is consistent with the paradigm of the neutral wind-driven, Eregion dynamo, and the E cross B drift that it induces. And here's where I'm stopping. Thank you.
Thank you, Ruth, for presentation. Does anyone have any question? You can either raise your hand, or if you type into the chat, I can read it off. All right, I will ask a question while we're waiting for anyone else. Ruth, have you compared the seasonal variation in, say, the winds from ICON with either the drift or the emission from gold?
Yes, yes, I have. Let me put this up. This was in my extras slides. So I only have the plot for 2020. I didn't make the wraparound for this. I did, and the bottom panel here is the green line wind. It's the ICON zonal wind at 114 kilometers. And all it does is just emphasize, the so-called, what I call the nonlinear effect, which is that there can be strong M2 zonal winds and weak drift and zero air glow, and there can be weak zonal winds and strong drift and strong air glow. So, and we see the same toward the end of the year here.
So Dan has a question.
Yeah. Hi, Ruth. The relationship between, I think you showed temperature and wind, right? The first two analyses, or the first, I forget what I think you were showing, but there were two different heights, right?
Okay, hold on a sec.
The temperature, both from the same satellite, but you're showing T and U, weren't you?
All right, hold on a sec. I accidentally opened IDL here, so I'm still presenting. I hope. Okay, let me go back into presentation mode. I did not dwell. I did not dwell on very much on the relationship between temperature and wind.
Yeah,
so
you are measuring two things, U and T, right? I mean,
well, yeah. Okay, hold on. All right, so I have, I do have the temperature at 160 kilometers. And I also have and I also showed the zonal winds,
right.
But I showed them at a different altitude at 114. And then I also showed them at 225 in the meridional winds. So I have not done I didn't show a comprehensive interrelationship between them, but ask away.
My question was just have those relationships between the temperature and the wind, do they match the sort of phase relationships and structures that you might get out of the GSWM, sort of standard calculation that I think Forbes probably did, when they were looking at SABRE. So are they consistent, I guess is my question.
I did not make any comparisons with GSWM, but whenever I could, I made comparisons with Wacom-X. And the variables that I could compare with Wacom-X, U, V, and T, look reasonable. So, that's the answer to your question. I did look at the vertical structures of M2 that I retrieved from Icon winds. It's just that I didn't show that. I didn't dwell on that in this presentation because I was kind of more interested in trying to show relationships among the I was more interested in focusing on the electrodynamics. But the recovery of M2 from in the winds and in the temperature looks quite plausible to me, and I calculated the degree of solar tidal aliasing that I feared, could be, muddying the picture, and found that it, at worst was on the order of 20%. That's not great, but it's the best that we can do.
Yeah, I was just curious because Wacom has everything in it, right? And whereas a simpler model that may just be did the relationship between T and U match what you might get from a Huff mode or something like that?
I have not looked at I have not examined the Huff mode. I didn't examine it in terms of in terms of Huff modes. I could try to do a Huff mode type projection with my gold retrieval, but it's really hard to do that with the retrievals from Icon, because Icon has a very narrow latitudinal range over which I can retrieve this. I mean, you may have noticed that all of my plots from Icon pretty much went from 10 degrees south to 20 degrees north. And that's it's kind of tough to that's not very much to work. It's not much to work with when you're trying to project onto global modes.
Thanks.
I see a question from Han Lee. Oh, good question, Han Lee. You know, I didn't even actually think to put those two plots side by side. And I think the answer to your question is that it depends on what. Oh, sorry. Let's get a better plot. I think the answer to your question, Han Lee, depends on which variable I choose to look at. If we look at the 1356 emission, then I would say that the seasonal variability of it is very nicely aligned with the cosmic, data that Nick shows. As I mentioned earlier, the relationships in some of these other variables are a little bit harder to nail down. It seems to be a little bit more. It seems to be a little bit, more, complex in the vertical drift, and in the field-aligned drift. I mean, the field-aligned drift also looks, kind of like Nick's cosmic seasonal variability, but we've got this. Unfortunately, we've got this big bite out in January, so it's hard to say. Although we are picking up the the enhancements, in the October-November timeframe. And in terms of the neutral variables, in terms of U, U in the lower thermosphere, as I mentioned earlier, the picture, the relationship to Nick's plot is muddier.
Oh, thanks, Ruth. Yes, I didn't realize the last emission. I mean the OI oxygen. Yeah, indeed, that's very similar. I was wondering, were you able to kind of, because of the question at the beginning you raised was how to reconcile the neutral wind seasonal variation in M2 with the variation of electron density, or MF2. So now after the reanalysis, were you able to kind of put that two together?
Well, what do you mean the reanalysis?
Sorry, at the beginning you said you showed the Hardy wind, showed M2 has a summer peak rather than just in the electron density only show a peak.
Yeah. Oh, I see. So that's another good question. So let me shoot back here. Let me shoot back here to the beginning. So I don't know. I really don't know, because if the E cross B drift mechanism is really so important here, then you would expect, then we would then I just don't know what I don't really know quantitatively what the relationship between, well, several things here. First of all, the Zhongforbes plot is with respect to geographic latitude, and perhaps in geomagnetic latitude, it might be these winds might reconfigure to be more favorably configured about a magnetic equator. I don't know. The other thing is that I don't have a good feeling at all for the relationship between the strength of the east-west wind and the electric field and the ensuing and the ensuing drifts. So I guess the short answer is perhaps I'm not. I haven't completely reconciled the picture, because with what we saw in Hardy, because I would kind of like to see. I'd like to see what this looks like with respect to magnetic latitude.
Well, thanks. I think, yeah, because the model can reproduce both features, it may be interesting to, to do some further analysis to look at that.
Mhm. Perhaps if I examine examine a lunar tide from a composite point of view, I can maybe get more coverage and see more. I mean, we now have, that plot that work that Forbes and John did. I think they probably used many years of hardy winds. I mean, you still have to be careful. You can't throw it all together and then start, looking for M2. You still have to work with continual segments of data to do the background filtering. But once you do that, you can still composite the filtered winds, the residues, and perhaps I can continue doing these analyses as more and more years of icon winds become available, and then I'll be able to say more, especially about seasonal variability.
Are there any other questions for Ruth? If not, then thanks, Ruth, for a nice presentation.
Thank you for having me. It was a pleasure.